In this unit, statistics is really getting fun, at least for me. Again, I am a statistics nerd. I really love this stuff. And this is where we're getting into some methods where we can do some cool things, and we can use these methods in a variety of ways in business and science and social science. What we have here on the slide before you are some pictures. The picture on the left represents materials testing the way it used to be done back in the old days. If they were testing the strength of a piece of concrete pipe, they would load it up until it failed. Because of inferential statistics, because of continuous probability distributions, they no longer have to do the proof testing like this that we see over on the left. Over on the right, you see a very unique bridge design. It doesn't look that exciting, but because it's got that curve in it, it took a lot of calculations to figure out how that bridge needed to be configured and what materials needed to be used to build that bridge so that it was a sturdy bridge that would last many years into the future. Whether you're talking about materials testing or bridge design or aircraft design and development or human resources or finance, continuous probability distributions are a big part of that, and the analyses that we can do because of continuous probability distributions is a big part of that. And we are in the area that we call inferential statistics. We really started inferential statistics with Unit 5 when we introduced different probability concepts. For the rest of this semester, everything we do really is about probability. We may not always talk about probability, but it's all based upon probabilities and probability distributions. But before I talk about continuous probability distributions, let me talk about, or let's review what we mean by a simple ungrouped frequency distribution. And I'll give you a couple of examples. I've got an example on this slide, and then I'll have another example coming up. Because our discussion of continuous probability distributions starts with our understanding what a simple frequency distribution is. When I say simple frequency distribution, we're talking about the frequency of occurrence for every possible data value for the variable that we're examining. For example, we can do a frequency distribution of store efficiency. If our analysis is store efficiency and we have store efficiency scores for 100, 1,000, 5,000 different stores, we can create a frequency distribution that will show the number of stores with an efficiency score of 55, number of stores with an efficiency score of 56, and so on. And here's an example of what a frequency distribution on store efficiency looks like. In this example, there aren't a lot of subjects, there aren't a lot of observations, so we do have some scores that where there aren't any frequency scores. But this gives us an idea of what we're talking about with a simple frequency distribution for the variable store efficiency. And we can do a frequency distribution like this for really any variable. Now, for the rest of the semester, most of the work that we're doing is going to be with variables measured on the interval scale and the ratio scale. We're not going to do much of any great importance with nominal and ordinal level variables from this point forward. Now, that doesn't mean those are unimportant, those types of variables. It doesn't mean that they don't have a place in analysis. What it means is we have limited time, and we're going to focus on methods that are used with interval and ratio level data. Another example of a simple ungrouped frequency distribution would be the frequency distribution of height in inches for every American over the age of 18. With this frequency distribution, we would identify the number of individuals 48 inches tall, 49 inches tall, and so on, all the way out to maybe 83 inches tall or 84 inches tall. Now, when we're measuring height, it may not make sense to go, I mean, you wouldn't need to include in your frequency distribution a category for those that are 8 inches tall or 12 inches tall or whatever. I mean, our bottom value might be 48 inches, or you might go down to 36 inches. There may be people as short as 36 inches, and there may be people as tall as, say, 90 inches, which would be 7 feet 6 inches tall. Or you could even go higher than that. But the idea is we're counting the number of people in each of these height groups. Everybody that's 72 inches, number of people are 72 inches, and so on. When we have that data and we graph it, it might look something like this. Now, these are sample data. The upper left-hand corner, we have a sample of 246 women and a frequency distribution of the heights of these women. In the lower right-hand corner, we have a sample of 511 men and the frequency distribution that's created. Again, height in inches, sample of 246 women and 511 men. And we see that the most common height for women is 64 inches, 5 feet 4 inches. That occurs with the greatest frequency in this sample. And this is also pretty close to what you find in the population. What we see here on this screen is also an example of how samples can be representative of a larger population. We'll talk more about the larger population and height when we talk about the normal distribution, because what we see here in this shape is what is commonly referred to as a normal distribution. For men, it looks like the most common height is 70 inches, and it's closely tied with, it looks like 70 and 72 inches have about the same frequency in this sample of men. Now, the average height of men in the United States, I believe, is 5 feet 9 or 5 feet 9.5. And again, we'll talk more about height. Height is a real interesting variable when we're talking about continuous probability distribution. So it's going to come up again, and we're going to look at some more height data. And you may be thinking, well, what does height have to do with business? Well, it depends on your business. If you're designing a car and you're selling cars, if you've got consumers that are buying your cars or furniture or whatever, there are a lot of products that are developed, manufactured, bought, and sold where height is a very important variable to consider. The height of your consumers is a very important variable to consider in your analysis. But again, another example of a simple ungrouped frequency distribution where we're looking at the frequency for each value in our data set. In this example here, we have the frequency of men who are 58 inches tall all the way out to the frequency of men who are 84 inches or 7 feet tall out of the sample of 511 men. And this is pretty much what the frequency distribution shape looks like for the larger population when we consider this variable. And here's another example of a frequency distribution, U.S. middle-aged male height distribution. It shows the most frequent height is 5 feet 8 inches. Now, over on the left hand, on the y-axis, these are percentages. Sometimes you'll see frequency distributions, tables like this presented with percentages along the y-axis. And then, of course, the percentages can easily be converted to numbers if need be. If you know the total number of people in your population or sample, you can use the percentages to convert 17% of men that are 5 feet 8 inches tall. You can convert that to the number of men that are 5 feet 8 inches tall. This would also be sample data, what we see here, but we do see what we would call the normal shape or the normal distribution occurring in this sample as well. Speaking of shape, every frequency distribution, when it's graphed, will have a shape. And you read about shape of distributions earlier in the semester, and I kind of skipped it. I saved it until now. I want to talk about it more thoroughly and more detail now. A distribution, the shape of a distribution can be what we call symmetrical, or it can be what we call a skewed distribution. And from your text, here's an example of different shapes that can occur when in our frequency distributions, when our frequency distributions are graphed. Over on the left, that's what we mean when we say we have a symmetrical distribution. Over here on the left, where's my pen at? Oh, there it is. Symmetrical. As we'll see here in the next video, when we have a symmetrical distribution like this, it's also referred to as a normal distribution. Then we have a positively skewed distribution. With a positively skewed distribution, the mean is going to be lower than the median, and then the mode is going to be at the peak of the distribution shape. Now, back to the normal, and I'll mention this again, but it's worth repeating. With a normal distribution, the mean, the median, and the mode are all the same. But when we start seeing skewed distributions like this positively skewed distribution, the mean and the median are different. And the mean is, I said the mean was less, the mean is actually greater than the median with this particular distribution. Negatively skewed distributions, the mean is less than the median. We might also, when we do our frequency distributions, when we create a frequency distribution and we graph that frequency distribution, we may also see this shape appear, a bimodal distribution. That's where there are two modes. And usually with a bimodal distribution, there's something going on within the data that needs to be explored in more detail. Now, for our purposes in this class, I'm going to talk a little bit more about positively and negatively skewed distributions, but most of our time in this unit is going to be focused on the normal or symmetrical distributions. Again, a skewed distribution is not symmetrical. We have a higher frequency of values to one end of the scale or the other. With a negatively skewed distribution, we have a higher frequency of values toward the higher end of the scale. Again, think of this as the x-axis, lower values here, higher values over on the right. So with a negatively skewed distribution, we have more higher values within our data set. Positively skewed distribution, same thing, but in a different direction. Again, same scale, we have low scores on this end, high scores on this end. We have fewer high scores in a positively skewed distribution. A positively skewed distribution can also be referred to as a right skewed distribution. A negatively skewed distribution can be referred to as a left skewed distribution. And there are some variables, household income being one, that tends to show up as a positively skewed distribution. You have a lot of households with lower incomes, but not so many households with higher incomes. And there are other key variables or noteworthy variables that may have a naturally skewed distribution. Not everything's normally distributed. What we see here, or what we've talked about so far as far as shape of the distribution, is an important reason for using histograms with our analysis. Histograms will show us if we have skewness. It will show us a degree of symmetry in our data set. Positively skewed distributions will have a single peak with values extended further to the right, with the mean value being greater than the mode and the median. And in this diagram, I like it because it shows the position of the mode, the median, and the mean. Remember, mode represents the value showing up most often. The median is the value that separates our data into the lower 50% and the upper 50%, and mean is the average value of our data. And again, their scale runs from low to high. Again, this is a right skewed distribution or a positively skewed distribution. Positively skewed distributions, as far as a natural data distribution that appears in some variables, they seem to be more common than negatively skewed distributions. And here is a negatively skewed distribution. Values extend further to the left, mean less than the mode and the median. Again, we have mean, median, and mode, and a left skewed distribution. Now, we can measure skewness in our data set using a statistical measure. Carl Pearson, the same statistician that developed Pearson's R, or Pearson's correlation coefficient, also developed a coefficient of skewness that we can use to measure the degree of skewness in our data set. And I'm not going to require you to use this measure or to do any calculations with this measure, but it's good to know about that there is a measure of skewness. Excel has a measure of skewness also. If you want to measure the skewness of your data, you can use Excel. But one of the quick and dirty ways of determining if you have a skewed distribution is looking at the mean and the median. Now let's go back here. If your mean is less than your median, then you have a left skewed distribution. In mean less than the median, you have a left skewed or a negatively skewed distribution. If your mean is greater than the median, then you have a positively skewed distribution. Now, in a little bit of difference between the mean and the median, that doesn't necessarily mean there's a major degree of skewness. But if there's a good degree of separation between the mean and the median, that's going to be an indicator of greater skewness in your distribution. Again, that's a quick and dirty method of doing it, of identifying skewness. But if you wanted a statistical measure, if you wanted a numerical coefficient, you could use Pearson's coefficient of skewness. And there are other coefficients, other measures of skewness as well. Now, Pearson's coefficient ranges from -3 to +3. It's not going to be greater than 3.0 positive. It's not going to be less than -3.0 negative. If your skewness coefficient is 0.0, that's telling you have a symmetrical distribution. A skewness coefficient of -3.0, that's a strong negative skew. +3.0, strong positive skew. But if you were interested in skewness, and skewness can be important to understand, you can use a coefficient like this, and you can also graph your data to get a better handle and understanding of what's going on within your data set. All right, that is it so far for this video. That's enough for this video. We've talked about frequency distributions, simple frequency distributions, and we've talked about how frequency distributions can have shape. They can be symmetrical, they can be skewed one way or the other. When we come back, we're going to talk about a special type of frequency distribution that is symmetrical and very important in the world of inferential statistics. It's very important in the world. So much of the world around us is built upon the knowledge that goes along and the methods that go along with the normal distribution. When we come back, we'll talk more about the normal distribution.